I appreciate being scheduled as a luncheon speaker because it guarantees, it's the best way for me to guarantee I'll have an audience. So I want to tell you about a undergraduate IBL sequence in real analysis that I've developed over the past few years. And I think this is interesting because it goes well beyond real analysis. What I'm going to talk about bears directly on the future of IBL and also on the future of public education. It concerns so not only real analysis, but public education, IBL, and even geometry. And I want to tell you how all these things fit together. So I need to start by giving you a little bit of background. This goes back for quite a number of years. My department, where I teach, has offered a 2-semester sequence in real analysis for our mathematics majors and our mathematics secondary ed majors. So this has been going on for quite a while, and these courses are taught regularly. And as an algebraist, I've over time had very little involvement in the past in the real analysis courses. We've had analysts who have taught them, and I was needed to teach other courses. So I didn't teach these, but they were taught often as lecture courses. And as a result, lots of students did quite poorly in them. And this became a problem for our secondary ed majors who have a tight schedule, and if they had to repeat a course, they weren't able to graduate on time. And so this became somewhat of a crisis. And what happened was that it was proposed that we eliminate the real analysis sequence from the secondary ed major and just give it to the math majors. Well, that was the point where I really got interested because I thought that was a very bad idea. It seemed to me that numbers and functions on the numbers are a central theme of secondary school mathematics, and that's where we can give pre-service teachers a background in those themes that they need in order to be able to teach them. Well, as it turned out, I was able to persuade my colleagues to drop this proposal, and the way I did that is I volunteered to teach the courses myself. That's usually the way to persuade people that you want something done. Well, so it worked, and so in order to prepare to teach these courses, what I did is I decided I wanted to review what it was exactly that K12 students learn about the numbers and functions on the numbers. I'd never taught there, and I thought I knew. And so I looked this up. I looked up in the Common Core standards. I read about those themes and just what is covered. And what I found there was fairly consistent with what I would have expected, but it was also instructive. And so I'd like to just tell you briefly about what I found there. So the K12 curriculum involving the numbers and functions on the numbers seems to break evenly between the K8 part, the early part, and the high school part. In the early grades, children learn about the counting numbers, and then after a while they learn about positive fractions and mixed numbers that fit in between those. And then at some point they add in 0, and then the negative integers and the negative rationals. And so by the end of the 6th grade, they're familiar with the entire rational number line. And they know that every rational number can be represented uniquely as a quotient of two relatively prime integers, and some of them can be represented as a finite decimal. And they also know if you give them two names for rational numbers, they can look at them and they can figure out if they represent the same number or which one represents a bigger number. And they can compute the sum of them and the product of them and quotient and difference. And so they all together have a solid understanding by the end of the 6th grade of the rational number system. And then as they go into the 7th and 8th grade somewhere, they start learning a little bit of algebra, and they learn how to use letters or variables to represent numbers. And that means that they can make quantified statements about the rational numbers. Like, for example, the distributive law. For all x, y, and z, x times y plus z is x times y plus x times z. And so they learn this kind of law, but also at this stage, they aren't in a position to prove anything like that. But what they can do is they can test it and get experimental evidence that it's true. They can take any three rational numbers for x, y, and z and compute the left side and the right side and see that they're equal. And by doing that, they get experimental evidence that it's true, which at that level is an appropriate way to substantiate it. And they also learn the other algebraic and order properties of the rational numbers, commutative, associative laws, and altogether what we would call an Archimedean ordered field properties. And these are just the properties of the numbers that they learn. And they call this a number line. So a number line is this set of numbers with all of these properties, algebraic and ordered properties. And so by the end of 7th or 8th grade, they have this very complete understanding of the rational number system as a abstract mathematical system. Now, when they go into high school, they extend the rational numbers to the real numbers. And so this starts out by identifying some other numbers that aren't described by their values, like the rational numbers, but rather they're described by some property they have, like the number whose square is 17, or the ratio of the circumference to diameter of a circle, or the power you raise 10 to get 41. And the transcendental functions give them other numbers like that that are described in terms of some property. The number whose log is 1. And as these numbers come up, they have no reason to think that there's a rational number that has those properties. And in fact, in most of these cases, we know there isn't. And what they learn is that, well, these are part of a richer number system called the real numbers that could be viewed as a solid line going in both directions like this, with a number representing each point on that line. And so this is the real number system. And they also learn that the real number systems have the same algebraic properties, like the distributive law and all of the Archimedean ordered field properties, so that the real numbers also form a number line. And so this is pretty much what they learn about the real number system in high school. And as they go through college, they really don't learn any more about it. They just use it all the time. In particular, they use the distributive law all the time in algebra. And if they graduate from college without taking real analysis, that's probably as much as they know. And what I found really interesting about this, so this is what kids learn about the number system and functions in K12. And what I found interesting about this is the contrast between the thorough understanding they have of the rational numbers in the early grades and the kind of understanding they have about the real numbers in the later grades. if you look at the later grades, for example, the distributive law there. The distributive law, when they're looking at the rational numbers, they could verify experimentally by just trying it out for lots of any numbers they wanted and see that it would work. But they can't do any such thing for the real numbers. Suppose they wanted to know, is it true that the product of the number's logarithm is 1 times the sum of the number whose square is 17 plus the power you raise 10 to get 41 is equal to the other side there? They have absolutely no way of verifying that. The only thing they could possibly do is take a rational approximation of each of those 3 numbers, and then of course they'd be the same because they're rational numbers. But they have absolutely no reason to think that that law is going to work beyond the rational numbers. They can't do any experiment like that to check it. But they have to take it as, they have to just take it on authority that this will work. Well, that would be okay if it was an isolated instance. But there are many things about the real numbers that they don't know and don't understand and have to just do as they're told. The rest of the Archimedean ordered field properties are the same. They have no way to do any tests on them. They're just sort of little gaps in their understanding of the numbers. And what I realized is there's just a lot of little gaps like this in their understanding of the real number system and the functions on the real number system. And as I thought about this, I started thinking about questions that you might ask a student about the number system that would make sense to a high school student. So questions that a high school student could understand, but the students entering my real analysis class, who are math majors, upper level, junior, senior math majors, could not answer. And so it seemed to me that these questions might give a nice basis for what they need to learn. And so what I want to do is show you some of those questions, because this is how I wound up organizing the course. I looked at these questions, and they gave me topics that I thought that the students then needed to learn about the number system. The first topic would be just a review of the rational numbers, as I've just given you, just as an example of a mathematical system that they really do understand, as sort of a model of what we're trying to do with the real numbers. We'd like to understand them like we understand the rational numbers. And so we looked through that, and we noticed that there's some numbers missing that we might like to have. And now here's some questions that I like to ask them. So here's the first question. What is this? 859, 859, 859, just repeating forever. What is that? And I asked my students on the first day. And this is something they've seen before. They might even see it in high school. And somebody even remembers and can tell me. And so what they say is, well, call that number x. And now, if that's x, well, then 1000x must be this. And if that's 1000x, then 999x would be 859. And so x is the rational number, 859 over 999. And I say, oh, well, that looks nice. That's a nice trick. Now, if we look at that, are we sure that we're confident that it's all correct? And so first, the first step was to multiply that repeating decimal by 1,000. And so are we sure we know how to multiply that by 1,000? If you give me a finite decimal, I'm sure that if I multiply it by 1,000, I'll just move the decimal over 3 places. But that's for a finite decimal. But what about an infinite decimal? Does it still work? Well, we need to understand how you multiply an infinite decimal by a positive integer. So, for example, do you know how to multiply x by 3? Well, what they would like to do is start on the right-hand end, right? That's how you multiply it, decimal by 3, but they can't find a right-hand end. So they don't know how to multiply that by 3. And so then I say, well, if you don't know how to multiply x by 3, are you sure you know how to multiply it by 1,000? that maybe is something that we need to understand here that we don't understand. And in fact, the problem here is if we want to explain why something is true about that x defined like that, well, we first have to understand what that means. What does that infinite decimal mean? And they don't know what it means. And so if you don't know what it means, then of course you can't know anything is true about it. So we need to know what it means. Well, we know what it means. What it means is you could describe x as being the limit of that sequence of approximations, of which are all rational numbers. That would be one description, or you could define it as the limit point, the unique limit point of the range of that sequence. So that's what we know. And so they need to be, this is what I would like to do. I would like to have them understand what that is from this definition, and then we'd be in a position to prove that these things are true, which they'll be able to do. So this gives some other topics that I'd like to include. Limit points, sequences, and infinite decimal expansions. And so I put those on the list of topics I'd like to have. Well, here's another question. What is the square root of 17? So they tell me that's the positive number whose square is 17. And so I ask them if they're sure there is such a number. And they can't quite tell me. So I say, well, is there an integer whose square is 17? No. Well, could there be a rational number whose square is 17? And we looked at that in a minute. And so we say, well, if there were, then m squared would be 17n squared. And now, what we want to do is apply the unique factorization to that. And so I asked them if they know about the fact that every positive integer can be factored, positive integer greater than 1 can be factored uniquely into primes. And when I tell them that's the fundamental theorem of arithmetic, then they agree they know about it. And so then we apply that here. And when we apply that, then we look at both sides of that, and we see that the left side, if you factored that, would have an even number of 17s, and the right side would have an odd number of 17s, so they couldn't be equal. And so there couldn't be a rational number that does that. Well, so that must be some real number. And now, referring to what we know, what real number is that? Well, here's a description of it. You could describe it as the least upper bound of the set of positive rationals whose square is less than 17. But now, in order to understand that and show that it's true, what do you need to know about? Well, you need to know about completeness, the completeness axiom and complete number lines. So that would be the next topic, to look at the completeness axiom and look at complete number lines. What else? Here's a question. What is the arcsine of 0.73? Well, they can tell me that the arcsine of 0.73 is the number between minus pi over 2 and pi over 2 whose sine is 0.73. And of course, when they say that, I ask them, well, you know there is such a number. And so they can look at the graph of the sine function. And when they look at the graph of the sine function on that interval, the number 0.73 is right about there. And so it looks like there ought to be a number right about there whose sine is 0.73. Well, are we really sure there is one there? Well, what we need in order to see that there is the intermediate value theorem. And in order to get the intermediate value theorem, we need to study continuity. And so continuity is the next topic, to look at continuous functions and then prove theorems about them, like the intermediate value theorem. What else? What is the log base 10 of 41? Well, they know that these are common logs, so everybody knows about common logs from way back. That's the power you raise 10 to get 41. And so we ask, is there some number y so that 10 to the y is 41? And if you look for a rational solution to that, could y be m over n? Well, 10 to the m over n, we'd like to know, could that be 41? And so they know what a rational power means. 10 to the m over n means the nth root of 10 to the m. And so if the nth root of 10 to the m were 41, well, that would mean that 41 to the n is 10 to the m. And that's 2 to the m times 5 to the m. But 41 and 2 and 5 are all different primes. And so again, this violates the fundamental theorem of arithmetic, which they all know about. And so there couldn't be a rational number, a rational power of 10 that gives you 41. And so y would have to be an irrational number. But now this brings up another problem. If y is an irrational number, well, they've looked at irrational power. They've looked at exponential functions back in high school and used them throughout college. They know all about exponential functions like this. They know how to take the derivative and the integral and use them to solve problems and so forth. So they know all about them. And so then I asked them, well, what does 10 to the y mean if y is irrational? Now you see, they know what 10 to the y means if y is rational, but they can't tell me what 10 to the y means if y is irrational. They're sure that 10 to the square root of 17 doesn't mean to multiply 10 by itself square root of 17 times, but they're not sure what it does mean. Well, in order to answer this, 10 to the y, if y is irrational, we can define that as e to the y log 10. And if we define it that way, then we can prove it has the appropriate properties and use it. But in order to understand that, what do we need? Well, we need natural logarithm. And in order to get natural logarithm, we need to know about calculus. So looking back at our list of what we need to know to answer these questions, well, we need to know something about calculus. So before we go back to the list, let's check and see if we know something about calculus. So I asked them if they know something about calculus. For example, do they know what this is? Integral from 0 to 3 of x squared. Well, sure, they can all do that. You take the antiderivative of x squared, and that's x cubed over 3, and evaluate it from 0 to 3, and you get 9. So they can do that. And I say, that's great. But then I say, I thought I remembered that the integral has something to do with area. And they say, yeah, it's a positive function. That's the area under the graph. And then I say, well, OK, but what does an antiderivative have to do with area? Well, I don't get much of an answer. It's surprising, but it seems that the fundamental theorem of calculus is something they learn in freshman calculus, maybe even in high school, and it sort of goes by quickly. And from then on, they use it to evaluate integrals. And at this point, they're stumped. They sort of think that there's two definitions of the integral. And try that with some seniors who haven't done this yet. It surprised me. So in order to straighten all this out, we need to know about the fundamental theorem of calculus. So now we can go back to our list. What do we need to learn about? Well, we add to the list continuity, then calculus, and then after calculus, we can do log and exponential functions. And then there's another sort of embarrassing question you can ask at this point. You have this completeness property in number 4, and then using the completeness property, you can develop continuity and calculus and log and exponential functions, and that's all wonderful. But then you might ask, the rational numbers are a number line that's not complete. So is there a number line that is complete? Well, we've been calling it the real numbers, but is there a number line that's complete? Because if it's not, then all this is a fantasy. It's like you could define a unicorn to be a horse with a horn in its head and then tell all kinds of stories about them, but they wouldn't be true because there aren't any unicorns. So this is somewhat the same, unless there are really some number lines that satisfy the completeness property, then all this stuff we've done is like stories about unicorns. So what we need is a real number line. And so here we can build the real number line and prove that it has the ordered field properties. Now, a final topic I have here is a short but fun chapter where we look at how much do you really have to add to the rational numbers to get the real numbers, and I call that the price of completeness. You got to add a whole bunch, right? You can look at that in terms of Cantor set theory and see that you have to add too much, a huge amount, or better look at it in terms of showing that the rational numbers really are measure zero within the real numbers. But that's a short topic. Now, all of this is all motivated by these questions that high school students would appreciate and understand, but college seniors who haven't studied it would have no way to answer them. And so this is quite a lot of material. I think what I found is the first 3 chapters and maybe into the 4th is a good first semester course, and then through calculus is a good second semester course. Sometimes maybe you can do log and exponential, but I had to go to another semester to do these other ones, and I had enough students who were excited about what they'd done to go on with it and do all of this. So there's a lot of material there, but I think there's a good first and second semester course here. Well, so what I'd like to do now is sort of step back from real analysis and look at how you start with what is a course outline here, or outline for 2 or 3 courses, but you start with a course outline like you might find in your course catalog that you're supposed to teach from. And how do you start with that and design a course? And so I want to step back from real analysis and say, well, what we have are 9 topics here. So suppose we just have 9 topics that we've identified. Maybe they come from the course outline of the course we're supposed to teach, and we want to design a course. So how might you go about designing the course? And I want to just describe 2 approaches that you might take depending on what you wanted the students to carry away from the course. So right here, I think of having 9 topics, and I think of under there a horizontal line that represented all the information about those 9 topics that you could teach. So imagine a solid line across here that represented all the material that you might teach under those 9 topics. Well, so this is just any subject. But what you're probably going to find is there's a lot more material there than students are going to be able to absorb and carry away with them. And that's generally true. So somehow what you have to do is choose some subset of that line of what you really expect students to take with them. And so here's 2 ways you might go about doing that. One way to do it would be to say, well, I'm going to teach everything. We're going to go from the beginning to the end. I want to teach everything and hope that they get as much as they can from it. Well, what they're going to be able to get from it will be just some small part of it, but it might sort of look like this. Like you teach it all, and well, they get just little bits all along the way. Okay? And so I would think of this as very fragmented knowledge. They know a little bit about everything, have a lot of buzzwords, but no depth of understanding of anything. You might describe this as a sightseeing tour of this entire subject. And that's something that, in some contexts, that might be useful. Like, I was imagining maybe if you're going to go and spend some time in Germany and stay there for a while, you might want to sit in on a course like this on the history of Germany. And you just get this sort of very fragmented knowledge that you'd carry away. You wouldn't remember most of what you heard, but you go there in Germany, and then you go sometime to King Ludwig's castle, and you sort of have an idea of where King Ludwig fits into the history of Germany, and it is nice. So that could be useful. But now, in a mathematics course and in my analysis course, this is not what I want. I would like to have students learn some significant parts of this that they learn in depth. But I'm obligated to cover those 9 topics. So what I want to do is pick out of each of those 9 topics some core material that they will learn thoroughly. And so in that way, it might look more like this, where they learn a complete, solid, contiguous piece out of each of those topics, some foundational piece of it. And so that I've covered all of the topics, I just didn't cover all the details in each one. But then I'm recognizing the fact that they can't carry away all of it, and if they can't, then what I'd like them to carry away is a thorough knowledge and understanding and mastery of a piece of each one. And I would describe this as contiguous knowledge as opposed to this fragmented knowledge. And you could describe it as a thorough learning of judiciously chosen material within each topic. Then you have the question of, well, how would you go about picking that piece within each one? And the way I like to do this, so this is how I've designed other courses. What I like to do is I like to look at each topic and identify some interesting provocative question about that topic. And then focus the study on that topic as learning everything you need to know to completely answer that question. And that's what you've seen here in the analysis case, a question about each of 9 topics. That's a fundamental kind of question. And then we study each topic by doing just what you need to answer that question completely and fully. So I have to find those questions, which is what I described in the case of the analysis. Now, if you look at what I've presented so far, what you see is that I've talked just about the content of these courses and what I want the students to take away from them. What I haven't talked about is pedagogy, of how to teach it. And this is the IBL conference, so I should be talking about pedagogy, right? Well, what I find really interesting here is that once you choose the content that you want, either the content on top, which you might want sometimes, or the fragmented sightseeing tour, or the contiguous knowledge, once you decide which one you want the students to take away from the course, then the pedagogy is really determined. There really isn't much choice. If you look in the first case, if you want to teach the whole topic, the whole subject, everything there is there, you don't have much choice but how to do it. You can't spend time messing around and having students coming up and talking about something and making mistakes. You just don't have time for it. All you have time for is to start at the beginning and talk as fast as you can to the end. So you have no choice in the first case but to lecture, and you need to lecture all the way through. And conversely, if you do lecture, if you teach a course entirely by lecture, particularly a mathematics course, a course with conceptual content, what inevitably happens is that there's an awful lot of little gaps in what you say that the students don't catch. And this is something a lot of people talked a lot about and written a lot about with respect to IBL, that when you lecture, As mathematicians, we know an awful lot, and we have an awful lot of very deep-seated knowledge that sort of is the culture of mathematics that we carry with us, that we use when we talk about mathematics. And so we wind up saying an awful lot of things that are just not second nature to students and slip by them, and they don't realize it at the time. But the end result is they go away with this kind of fragmented knowledge. So if you ask them later what you said, they'll just have all these pieces that they can't fit together. In contrast, if you don't lecture, well, then what you have to do in class is something else. If you're not talking, you've got to have the students doing something. And so you have some kind of an active learning pedagogy, which means some form of IBL. And I've found that if I use IBL, that then it has to come out like this. I've had colleagues who lecture tell me that, you've heard this, that they'll say that, well, you know, I taught this course and I explained everything really carefully and really clearly. And all these weeks, I just explained everything really carefully and clearly, and then I gave an exam. And you know what? The students didn't get it. Well, I've heard that. And what I've said is that the way I teach, that can't possibly happen. It can't happen because I can't walk out of my class with any illusions about what my students do and don't understand. I'm standing there listening to them talk and explain what they did. And so I see all of the gaps and all of the problems and all of the misunderstandings. And those are actually valuable because they form the basis of a class discussion. And in the end, we, one way or another, work that all out. And we don't go on to another topic or another problem or another theorem until that one has been completely understood in detail. So this really forces, the IBL pedagogy really forces this kind of, well, you can see it, the little blocks, the contiguous learning. Whatever you're talking about, whatever you're studying, you have to completely do whatever you do. And so IBL gives you these kind of contiguous blocks of knowledge. So if you look at those two, the lecturing approach and the IBL approach, as I say, lecturing does give you this sightseeing tour of everything. IBL gives you this thorough, deep understanding. There are advantages and disadvantages both that are worth mentioning. I think that the biggest advantage of IBL is that it really empowers students to reach their full potential. And you'll hear a lot in these talks about why that's true. If a student has gone through and understood the core content of one of these topics, well, they're not learning that whole topic, they're just learning that piece, but they're learning it in great depth and thorough depth. And what it means is two things. One is that they have the foundation, so at some time in the future, they may need to know more about one of those topics than was taught in the class. But what they have is two things. They have the foundational piece that they need to build the rest of that topic, and they've developed the skills to know how you build mathematics from a core of understanding. And those are the two things they need to fill it out, so they can extend their knowledge beyond the course later to learn whatever they need to know. And that extends beyond this course to other courses. They can build mathematics in the same way, and they knew how to think and build ideas so they can apply that to anything. So you're empowering them to do a lot of skills that go way beyond the course. And this is why I think IBL fulfills Ed Berger's 20-year test. 20 years later, these are skills that they carry with them. And in contrast, if you look at lecturing, what happens when you lecture? Well, students, what do the students take away when you lecture? They take away what you told them that they remember. And so student knowledge, when you lecture, is limited to what they've been told. They can't go any further with it, again, for those same two reasons. They can't fill in the spaces there because they don't have any contiguous piece of it that they fully understand. And also because they don't know how to build new knowledge because they haven't done that. And so, well, IBL is empowering to allow them to learn more later. Lecturing is limiting them to just learning what you told them. So that's a definite advantage. I mean, that's why I think IBL is so good and why I like to do it. But actually, lecturing does have an advantage that I just have to mention. It's really economical to deliver. If you have a course and you're just lecturing to 25 students, say, well, you could just as well be lecturing to 250 students. It's all the same to you, and it's all the same to them. And then the cost is 10% of what it costs to lecture to the 25. And in fact, in the modern world, you can do better than that. We have now these MOOCs. These are the massively open online courses where major universities will get their best teachers to record an entire course, put it online, and put homework online, and put tests online, and automate the whole thing. And then instead of having the course go to 25 students or 250 students, they can deliver it to 25,000 students at a time. And the cost per student is almost zero. And so lecturing can be very, very economical. And in contrast to that, and that's really important in the modern world where the cost of higher education is becoming a real issue. And there's a lot of concern about that. And student debt is a big problem. And so if higher education, if student credit hours can be delivered cheaply, well, that has an advantage. In contrast, IBL is expensive because you need a real live instructor with few enough students so the instructor can interact with each student and work individually with students. And so you can't do what you want in IBL with these huge numbers. And so this distinction actually, these MOOCs, they actually are a worry for some of us who want to earn a living teaching. If universities are going to save money by eliminating faculty and delivering student credit hours with MOOCs, that is a worry. But you know, I think there's a bright side of MOOCs. And the bright side of MOOCs, from my point of view, is that if you're teaching class, you need to be able to tell your students what it is you're offering them that they couldn't get just as well from a MOOC. And you need to be able to answer that question. And if you're using IBL, then you really are offering them something that they can't get from a MOOC. You're really empowering them and giving them something that will last into the future. And if you're lecturing, if you're just lecturing, then you really don't have any answer. And so I think that this advent of the MOOCs is a real positive indication for the future of IBL. That if nothing else, doing IBL is a form of job security. So, so I encourage you to use IBL for whichever reasons ring a bell with you. Okay, so I want to wrap this up by going back to K12 mathematics, because everything I've said turns out to have some interesting implications for K-12 mathematics. And so if we look at K-12 mathematics, I would say that the central theme of K-12 mathematics is the number system and functions on the numbers, that is a central theme. And if you look at, so I'll just call it the number line, what we learn about the number line. And we've seen that we can describe what students learn about the number line in K-12 like this. In the early grades, they get a very thorough, contiguous understanding of the rational number system. Okay, I described that at the beginning, and I'll indicate that by a little solid line there. So a contiguous piece of the number line, namely the rational number line, that they understand thoroughly. But then, as we saw, if you look at what they do in the rest of high school with the number line, they learn a lot, they can do a lot, but what they learn is all fragmented. It's full of holes. So it looks sort of like this, of what they learn in high school about the number line. Now, I actually don't mean to criticize K-12 mathematics in how they handle this subject, because this is really unavoidable, as I've described it. Students need to learn about the number line and functions on the number line for all different purposes if they want to go on with their education. Anything quantitative, they need to know about it. And filling in those holes is a matter of real analysis, which is not accessible at the high school level. So there's really no way they can avoid that, but that is what the picture looks like. And what's unfortunate about this is it is unfortunate to send kids away from high school with this idea of mathematics being about having to learn all kinds of things that you're told that you can't possibly understand or justify, and just doing what you're told. That really is not what we want them to take away as a conception of what mathematics is about. We'd like them to come away thinking that mathematics is something you can understand yourself and build yourself. And so traditionally, back in history, there was a solution to this. And the solution was that the second most important subject, theme of high school mathematics, was geometry. And geometry is different in this respect, that you can understand it. In the early grades in geometry, students learn about shapes and sizes and names for them, and they find out that certain classes of shapes can be described by certain properties. And those properties have relations to each other, and that lead to precise definitions. So you can define something, a class of objects like parallelograms, by certain properties, or circles or squares. And just being able to define classes of objects precisely with properties is fundamental to all of mathematics, and in fact fundamental to an awful lot of thinking. And that's what they get in the early grades in high school in geometry. It's like a little contiguous piece that they learn. Now, what happens after that in geometry in high school? Well, it used to be that students studied Euclidean geometry from Euclid's axioms. And Euclid's axioms were designed so you have these axioms and you build from those axioms and logically build geometry, all the facts you need to know in a hierarchy that where you can understand everything because you work it through yourself. And that is the kind of image we want them to carry away about what mathematics is. And so geometry was able to balance this fragmented knowledge of the number line. Now, there was a problem with Euclidean geometry. Euclid did this in 300 BC, and there were a lot of problems with it as mathematics became sophisticated in the 18th and 19th centuries, and people looked back and realized that there are two problems with Euclid. One is that there were logical gaps where there were statements being made that weren't weren't using the axiom, so assumptions that weren't being stated. And the other thing is that he couldn't really make a complete theory. He couldn't really talk about things like measure of lines and areas because he didn't have the real numbers. They just had the rational numbers. And so it wasn't, so it was both had these logical gaps, and it was incomplete just because it was built on what was known in 300 BC. And in the late 19th century, all of that became clear finally. Mathematicians understood geometry, the role of the parallel axiom, and particularly they learned about the real number line. Everything that I want to teach about the real number line was developed, finalized in the late 19th century. And so it would make sense then to try to reformulate geometry using the great discoveries of the 19th century. And that was done initially by Hilbert, but Hilbert's system was very abstract and not useful in schools. And so another way of doing that was discovered by George Birkhoff in the 40s. And what he did is he introduced a new axiom for geometry. And this is an interesting axiom because until I got involved in this recently, I never heard of it. But anybody in this room who's took geometry in high school since about 1980, which is the majority of you, probably are familiar with it. It's called the ruler axiom. And the ruler axiom says that every line looks just like the number line. So it's a basic axiom in geometry. It was adopted in the late 70s. It's in all the geometry books that are used since. And the ruler axiom says that for every line, you can coordinatize that line, give every point on it, associate each point with a number, and so it looks just like a number line. Now, if you know that every line looks like a number line, then what you can do is you can say, well, take two perpendicular lines like this, where they cross at 0 on both of them, and now you can take any other point out here and drop a perpendicular to both of those lines and see where it lands, and you get a pair of coordinates for that point. And so what that means is that the plane that you're talking about looks just like the coordinate plane. So using this ruler axiom, it follows that the plane you're studying is just the coordinate plane. And when you do that, then you realize that, well, geometry, then you don't really need any axioms because you know what the plane looks like. So the axiomatic approach sort of falls away because you've just got it. You know what it is. And what happens is that algebra and geometry merge, and you get what they called integrated mathematics, which is algebra and geometry mixed up together. And this was introduced around 1980, and they changed the names for it, but it's still the same thing. As long as you have the ruler axiom, that's what you're doing. But particularly what was lost in geometry is an axiomatic buildup. And in fact, if you look at this idea of teaching geometry with the real number system as the foundation, then you can see that there's a bit of a problem, because the student's knowledge of the real number system looks like that. It's full of these holes. The foundation of it is full of holes. And now if you use that to study geometry, then what does their knowledge of geometry look like? Exactly the same. And so in both cases, what they learn in high school is just built on this foundation of stuff they can't really understand. And so what I propose is that geometry be done not by this paradigm, but by an axiomatic approach that is similar to what Euclid did. And that's why I spent several years writing this geometry book, which does that. So this is an axiomatic approach to geometry, which uses the advances of the 20th century the late 19th century, but doesn't use the number system. And so it can be done exactly in the spirit of Euclid, but it's both complete, logically complete, and complete content-wise. And what I would hope is that that would be done in the future, that geometry could be taught this way. And there's no reason why it couldn't be. And then what we would have is a picture like this, where students learn about the number line. Well, they can't learn real analysis in high school, but they could learn geometry in a contiguous way, so that they would come out of high school understanding what it really means to understand mathematics and to do mathematics. And they could be told that the number line can be understood in the same way, it's just a more advanced topic. Now that last statement is hard to make if you're the teacher and your understanding of the number line looks like that. So what I say we need to do is we need to teach the number line to pre-service teachers in a way that they will understand it as a contiguous system. And that's what I want my real analysis course to do. And so what I would hope in the future is that teachers would learn about the number line like this through a real analysis course. There's a lot of good real analysis courses, IBL courses out there. Mine is specifically focused on this. But if the high school teacher would learn about the real number line like this, then we could be assured that there was somebody in the high school classroom who understood what couldn't be taught there and could reassure the students and answer questions, and that the students could come out taking geometry like this and having that as a model of how mathematics is really supposed to work. So I have the notes for my course in analysis available now, and they're in the showroom there, and I think they ran out, but you can put your name on if you'd like to get one, and I'd like to invite you to pilot test it and give me your feedback and ask for my advice, and join me in this project to try to revise how pre-service teachers are prepared. Okay, well, thank you for letting me interrupt your lunch.
I want to thank you for your comments, particularly about thinking about how we motivate the content of courses through the use of questions and other inquiry approaches to curriculum in the first place. I really appreciate that, and I think this community is well served to think about curriculum as well as pedagogy. I appreciate the reminder. I loved your visual of the two different, how lecturing and IBL might be visualized in terms of what understanding students take away. I do want to offer a third visual that I think is problematic, and I was wondering if you could speak to it. And that is, I think sometimes in IBL instructors take the approach of wanting contiguous knowledge, but with absolutely no gaps. And so the entire course ends at topic 3. Do you see what I mean?
Yes.
Right? And so I was wondering if you could speak to how do you help motivate particularly newer teachers to just at some point stop and go on to the next topic?
Sure. Well, what you have to do is look at the time you have and look at the students you have and see what they can do in the time you have, and then make a judgment about what can be done. Then the question that you're asking is about how much do you really have to cover? And sometimes in the IBL course, what is good to do is if you really have to cover more than you think you can cover in this contiguous way, is you can identify some pieces which you'll just do by a quick lecture. And if you go through and you teach an IBL course and you teach the foundational chapters in a way that is thorough and really get the students proving theorems or solving problems on their own so that they really understand how that works and know what it means to do that, then they're in a position where you can say, now I want to tell you about something else that we aren't going to take the time to go through that way. And you can often run through a lot in a very short time. And now you've said it, they know that that's there, and now you do what you can in the time you have. So, does that help? Sure. Okay.
Hi, David, Mike Starbird. First of all, I wanted to tell everybody to use his geometry book because it's wonderful. But I did have a question, and I love your metaphor and your diagram of things. And so it occurred to me that maybe we should be thinking about how to have these, contiguous things with dotted lines, and then at what stage could the dots be connected? In other words, is there a role for the dotted line creation, just the highlights, but then where is the next potential step where it's not just contiguous bits, but where it actually connects the knowledge? You follow me? In other words, maybe our community should say, when should we actually, maybe we should think about how the mixture of IBL kind of experience that is more deep and contiguous, which we all love here, and yes. I certainly do, but then having it fit in a systematic and thoughtful way to having the dotted lines and then filling them in some systematic way. And I was just wondering if you had a comment on that.
You're thinking of presenting the dotted line version quickly and then going through more carefully?
Yes, and not necessarily in one course, but I'm just saying our conception of the whole mathematical education of a person, should we overtly, for example, advocate for some courses that do just give the dotted line, but with the expectation that we're going to have them filled in and become more complete and robust at some later time, as in fact all of us have done when we had a vague understanding of many topics, and then we later went on to learn them.
Yes. So yes, and an example of that would be teaching high school kids about the number line, where there's no choice but to teach it to them like that. Yet they need that, and they need it in all kinds of places. And so we are doing just that then, and we have no choice. But then what I would like is to have the teacher have the dots filled in and be able to speak to that and say just what you said, that this can be done in a more advanced course. So that would be an example of what you're saying, and that happens sometimes. Sure.
So let's thank David Clark.